client entered my studio and said, "How much is this going to cost me?" Because he said, "You know what BOAT stands for, right?" And I turned to him and I looked and I said, "Buoyancy Operated Aquatic Transport?" And he said, "No, BOAT stands for Break Off Another 1,000. Hello and welcome to Raindrops in Virginia, and on today's job we had a stainless steel hydrofoil from a wake boat come in. The client came to us to have this fixed. They were using it one day and they had hit the wake of another boat and had a slight side load on it. Realized that the boat had changed, and it took the driver of the boat most of the lake to turn around to go pick up the boarder, mostly because of their new bent up rudder that was larger than their existing rudder. Client told us that the previous owner to the boat left this down and accidentally ran it aground one time as they were loading the boat. So we can see that through the scratches on the front of the actual foil itself, but as you can see, there's quite a bit of damage to this, both stress and an actual knock. This boat is a 2013 Malibu Wake Setter. It is a specialist boat that is used for wakeboarding, wake surfing, and general pull-behind sports, water skiing, and so on. This is the actual boat that the foil came off of, and this foil broke in the down position, and then they folded it up. And the client had tried to bend it back so he can get it off. And as you can see, it folds up above the transom so that you can reduce drag. When the foil is up, as you can see, the boat is rolling quite smoothly, quite nicely. But when the foil is down, it forces the back of the boat down, making it a little more inefficient, but making it act as a larger boat, giving you a nice, crisp, two-faced wake that you could then do tricks off of. And you can also create rolling waves that can be used for wake surfing, whereas you don't need a rope as seen here. So we start this project as well, every project starts by making some either tools or accessories. And here I'm taking some 304 stainless nuts, 304L, boring out the inside so that I have some rather accurate spacers for the perimeter of the frame fixture that I'm going to be making for it. Here I am changing out the carbide. You know, I've made a couple of these, and often I'll make a tool, I'll use it, and then store it, and it ends up coming in handy later. But I've never had a project or a job where I haven't need to make accessories or tools. And here we are at the main studio at the fixture table, and I don't always cut and grind on the fixture table just to keep it accurate. But this was a special case because we had a polished bottom and I didn't want to damage anything, and I really want to keep it straight. So we use a dedicated grinding equipment, dedicated wheels, brushes, and everything for stainless steel, because you can quickly contaminate any stainless steel. So if you're grinding steel or aluminum and then you go grind stainless steel, you'll notice in your welds there's a great deal of contaminants. And so we try to mitigate that as much as we can. You'll see as I'm working that I keep everything clean by blowing it off, because that can be a problem as well. So here we're using a straight cutting disc and then an asphalt aggregate disc to grind it close. I'm getting to around 2 millimeters, and then we'll finish with something a little finer. The underside of this part is polished, so I wanted to preserve that as much as I can, so that's why I'm grinding on 2 mechanics cotton towels. And if it begins to burn, it creates quite a smell, so that helps out. So as we can see, I'm here at 2 millimeters, and in aerospace, this root would be penetrated. Now, this is a production part. This is a very good production part, but as you can see, the root is not penetrated. It's TIG welded rather quickly, and angles maybe weren't quite right. The heat wasn't quite right. And so this, in aerospace, this would be a full penetrated weld, but in this case, this is not. So all we have to do is grind out the weld and really lift out that ring. And you'll see me with my pick tool to just peel that on out, and it was only maybe 5% penetrated in that root. And so in that case, there is some warp because we feel for this part, TIG welding might be a little too slow because stainless steel is such a poor conductor of heat. So in this case, we will be using GMAW process, or gas metal arc welding. And the reason for that is you have two parts here. One, the plate underneath is 3/8 of an inch thick, and the tubing wall thickness is roughly 1/8 of an inch, a little under that because it's metric. And so you have some pretty big size differentials going here. One part is going to be overheated. This part broke at the ending heat affected zone of that pipe up there, if you go back and look. And we're trying to mitigate that. So with GMAW, we can point where we want our bite, where we want our heat, quickly and efficiently, and then get in there, lay the bead, and get out. It's not the prettiest thing. It's not as pretty as TIG welding, but we don't have a weight issue here. We don't have a prettiness issue here. We just need to get it in there and get the job done. So now that we have this part free, I'm going to square it in at the disc grinder, and just to make sure everything's square. And you'll see me also put in some center sight lines just to make sure everything's even, so that I don't have any problems with a center balance when I fit it in the jig that we eventually make. So whenever I'm in production for a part, or I'm going to make a lot of something, I will go ahead and do a metal jig, something that's durable, something that can be survivable. But for a one-off part like this, I tend to just do wood. It is accurate enough for what you're doing, especially getting an angle out of something. It holds tight, especially when it's fastened down to a fixture table. It is just fine. You just have to watch burn. So here I am swapping out our steel wire. Now off camera I changed the gun liner because that is a contaminant as well. We have a dedicated gun liner for that. Here I am using a Harris 308L because we are welding 304L. The reason we go with L is it's low carbon for low carbide precipitation. That's pretty important, and the shield gas we're using is a heavy helium. That is Shield Pro 554. That's 90% helium, 7.5% argon, and 2.5% CO2. And that I found to be the most effective for stainless steel, especially for near spray. We're very high up in the range because I tend to go pretty quick on stainless steel because of that thermal conductivity. So that cutter we just finished. I really like that cutter. It's made life so much easier. Now on all of our cutters, including that one and this disc grinder here, everything is new, and again, all dedicated cutters, because you do not want to share materials or embed anything into those cut surfaces, because that just makes your life miserable in the end. But you know, if you keep everything clean, then you'll have a lot of success in anything that you're doing. And I remember one professor years ago tell me that clean it, and when you think it's clean it again, and when you think you're done, clean it one more time. And I've always lived by that rule, and it's always really helped me. So here I'm clamping the two together, and I'm taking the blade and scribing a very sharp line to copy that angle, so I have two pieces that are pretty well exactly the same. Now on the angle grinder I'll high cut, and I'll come back to the disc grinder with, again, a new disc there, so I don't have any contamination issue, and I'll bring it right to the line, because I don't try to cut with the angle grinder straight to that line. You'll always have mistakes, it'll never be straight. And you saw there that I used the jig to get myself the hole for the actual the fulcrum hole for the entire foil itself. And now I'm binding the two together. Now that I have that pilot, I can go ahead and go to the drill press and make both of those, just machine both of those together. So in this case, I didn't have an annular cutter or any carbide cutter in either high-speed steel or carbide or anything like that. So I'm using this bimetal hole saw, which gave me a good amount of length, but also gave me the size I needed. And if you treat them right, they're not bad. You need to watch wobble, and you need to be gentle with your cut, but in this case, they do quite an effective job. This drill press I received it as a gift when I was 12 years old, and it was my very first drill press, and I've always had it with me, and it's always my go-to press. It's a very small one. It's not the most expensive, but it's just one that I always think of, the one that it's just my go-to press. It's one of my favorite, and I've really done nothing to it but maintenance. I think it's received a new belt. I've redone one bearing. Its motor is still fine. It's just been a really great piece of equipment over the years. Now these bimetal bits, they do heat up, you'll lose the paint, but you have a bit of life left on them. They're quite, like I said, they're quite efficient. Here I'm cutting the material for the fulcrum connection for the foil itself. We just drilled the holes, and these will suit inside that hole so that we can bolt through. The originals were roughly a little over a 1/16 of an inch thick, which I don't feel is quite thick enough, so we've done a very thick wall on this tubing. And if you look in the beginning, there were cracks that had formed all around the throat of this eyelet. Strictly because this is a high-stress part, and the steel can only do so much with this level of stress. I mean, chromium is chromium, steel is steel. It's just going to do what it's going to do, especially under these stress loads. And honestly, a part like this you can consider is a consumable. Here's where the fixture table really earns its keep in keeping everything straight, because stainless steel, again, the chromium content in it, it is an extremely poor conductor of heat, so the warping is very, very bad. So you really have to baby it in terms of keeping it straight when you're putting this level of amperage and heat into it. You can see how it's really belt and suspenders construction here in terms of fixturing, where anything I can tie down, I am tying down, because you don't want it to warp. Once you've warped, you really throw away the part. You can see during this weld, I'm getting in and getting out, just applying my heat where it needs to be and then moving along. The trick with these welds is your tie-in. There is some backstitching similar to TIG welding, but you can see how the heat affected zone is much smaller because you're punching it so hard. Whereas with TIG welding, you have to sit for a few seconds and establish the puddle on both sides facing what you're trying to join, and that's when the heat builds up a little much. And even on chill blocks, weird parts like this, it doesn't pull enough heat out. Welding stainless steel is not very different from welding mild steel or carbon alloy steels. There are just a number of different avenues of problems to be aware of, and understanding common defects that can occur is a big step to mitigating them. The first item we need to understand are the 5 basic types of stainless steels. There's austenitic, ferritic, martensitic, precipitation hardening, and duplex. In this case, we're welding an austenitic 300 series alloy, which is a lower ferrite face-centered structure, whereas it becomes stainless via the development of a very thin layer of chromium oxide. And the nickel content helps to speed up the development and as well harden this transparent protective layer. But with stainless alloys, we can see some defects that form rather readily. One most notably is cracking. Because austenitic steels lack ferrite, which dissolves and homogenizes detrimental impurities that result in cracks, you see an increase of this defect similar to high carbon or even alloy tool steels. And there are ways to prevent this, first by decreasing outside contamination, second by controlling the heat affected zones as much as you can, and third intrinsically by selecting a filler material that contains higher ferrite to mitigate or even dissolve those detrimental impurities. You do have some things against you with austenitic stainless steels. One example is with a lot of high carbon steels, you can mitigate cracking by preheating, welding, and then allowing the media to cool rather slowly with shielding blankets or part ovens if the size of the part allows. With stainless, this is just not really possible due to the differential grain coarsening, whereas the material grain actually becomes coarser in certain areas, which is why you have such fatigue breakage at the end heat-affected zones of a weld. And also because of this high chromium content, you have chromium carbides that are created as well within those heat-affected zones, which is exceptionally hard, further complicating the differential grain coarsening of that media structure. Back to the project, I have installed a threaded rod so that I can lock in a set width between those posts for that eyelet plate at the top of the piece. And so now from there I can also use that threaded rod to set my A and B axis from the actual foil itself. And so you can see here also putting a block down at the bottom to set my width again to keep everything very straight, and I'm locking everything in via its coordinates. I usually take coordinate because for me it's a little easier for my brain to work from actual coordinates instead of measurements that you took off of a potentially mangled piece. So in that case you can almost reverse engineer whatever it is you're trying to recreate so that everything fits right, instead of taking measurements off from an already bent piece and you're hoping that it's correct. One thing you'll see me do a lot is I'll use anti-spatter spray to mitigate spatter and to mitigate iron contamination, and I will use a chipping hammer that is a stainless chipping hammer, again because of either iron smear contamination or damaging that chromium oxide face-centered protective layer that stainless steel grows. But the most important thing about an anti-spatter spray is it has to be carbon-free, because otherwise you're just pouring more carbon into that weld and to the weld joints, and in effect it becomes a contaminant. And again, I can't stress this enough. Make sure any tools you use to prepare stainless are only used to clean stainless. For example, if you use a stainless steel brush to clean carbon steel, don't use it again on any stainless steel. This is also true for stainless hammers, picks, and clamps. Trace amounts of carbon steel can transfer to the stainless, causing it to rust. As well, to this grinding carbon steel in proximity to stainless steel can result in similar issues. This is known as iron fallout contamination, and a great example of this is in the automotive detail industry, where a car located in or near a city or even a train yard, you start to see rust spots on the paint that eventually work through that paint. Carbon steel dust suspended in the air can land on nearby stainless steel and lead to corrosion. This is why it's a good idea to keep carbon steel and stainless steel work areas separate, but that's not always possible for a lot of shop spaces. Back to the project. With TIG welding, you have this wonderful ability while you're welding and you're finishing a weld to backstitch over the end of said weld and to avoid a crater crack. With MIG welding you can't really do that, so you'll see me here, I'll pile extra at the end of the weld and then grind it down so I don't get that crater crack. And you end up with a really nice finish, but at the same time with a part like this, you have to be excessively careful with the harmonics, because you're now in the realm of dealing with a great deal of fluid dynamics, and this part basically is a harmonic tuning fork. And over time you can see very strange things happening in terms of the stresses and in terms of things opening up that really shouldn't be. So you really have to dot your I's and cross your T's in terms of your trade craft and keep everything very clean and very neat, because whatever you have on there is going to wiggle loose, either by cavitation or by just general flexing. And that's the fun part about metallurgy and about engineering in general, is finding those happy mediums and those compromises in getting the minimal amount of materials out of it, but at the same time solving certain problems like using a face-centered structure, austenitic stainless steel, so that you don't have issues with paint, you don't have issues with corrosion. And that's just always the part that I've really enjoyed about general metallurgy and engineering is solving these problems, and it's always been a lot of fun. This is the part where in the project the prep work really pays off, where you have nice finishes, you have nice cuts, they're stable cuts, and now I'm drawing in my layout lines, getting everything in, exactly dialed into where we need it to be, having good layup, and nothing wobbles, and it's just a nice fit so that I can draw my lines, and I'm now scribing my lines in the ketone markers so that I get very precise fitment, because again, you don't want in this part with it dealing with water and it being such a harmonic part that it is, you have full balance and everything is done right, because the more you can decrease vibration, the more you can decrease incorrect angles, you don't have issues with cavitation and harmonic vibration that further breaks other structures within the vessel, or especially the part itself. But just right now I'm getting my tacks in so that I can then get this into a very good position to lay a really quick bead and just again get in with that weld and get out. And because you don't want to overheat any parts, you just want as efficiently as you can. And you'll notice also as I'm doing my layup and my tacks, I check things 2, 3, or 4 times because I have a confirmation bias the size of a truck, and with a part like this, that's always a good idea. And so I'll lay in tacks, as you can see, but then I'll grind them down to keep their profile low so that I don't overgrow a weld bead. And I'm just triple checking everything, laying in my tacks, and now we're pretty well fixed, but I'm always watching those sight lines. I'm always watching where I am, what I'm doing. And here are my last 2 tacks. Now I'm just going to finalize my measurements and my angles, because this is a time when I can fix any problems that I see, and then we move on to cleaning, and a lot of cleaning, and that just sets yourself up for success. And now we're going to get the piece into a desirable angle so that we can get a rather easy torch angle, because we want to bite into that thicker metal a lot more. We don't want to ignore the thinner metal, but we want most of our amperage bite into that thick metal. And here I'm cleaning off the soot, and then again I'm moving very quickly, and because again we're near spray, and we're not quite at spray because the sound's not right and the gases aren't quite right for spray. Next we're going to be passivating the stainless steel. ASTM A380 states that the process of passivation is the removal of exogenous iron or iron compounds from the surface of a stainless steel by means of a chemical dissolution, most notably by a treatment with an acid solution that will remove the surface contamination but will not significantly affect the stainless steel itself, for the purpose of enhancing the spontaneous formation of the protective passive film. In current industry practices, there are currently 3 types of mild passivation oxidants utilized. The first being nitric acid, the second nitric acid with sodium dichromate, and the third being citric acid. In this piece we shall be using citric acid, as it can be a safer alternative and does not require special handling or regulatory oversight, and it also carries an added benefit that it is easier to control reactions under differing temperatures, as it functions and is not susceptible to media etching known as flash attacks. It also does not corrode other equipment around via vapor travel like nitric acid is certainly capable of doing. Another reason is that it is more environmentally friendly, as it does not emit nitrogen oxide vapors that contribute to smog and acid rain and affect the ozone layer of the atmosphere. As per ASTM A967, we prepare a 5% by-weight solution of citric acid into water and a soluble gel agent so that it is able to cling to vertical surfaces, and we let that solution dwell upon the surface for 30 minutes at minimum at a surface temp of around 75 to 80 degrees Fahrenheit, or roughly room temperature. We then base out and clean off the passivation solution and allow the piece to sit for about 24 hours so that the chromium oxide layer can develop and we can fully utilize those properties. I would like to thank everyone who has made it this far into the video. I know this is a lot of information to take in. I'd also like to mention that I am in no way knocking TIG welding. If you want to learn more about stainless TIG welding, check out Jody over at weldingtipsandtricks.com. There will be a link in the description for his page.